Thank you, Mr. Chairman, for the kind introduction. All of our Hall magnetic sensors do have a temperature sensor in order to compensate for their sensitivity and offset thermal drift. In that way, temperature is transmitted to the output of the Hall sensor. This is the background of the work I'm going to present here in the following way. I would like to explain our motivation, followed by the design and layout of the temperature sensor, the experimental results, and our conclusions. First of all, our motivation is to minimize package stress effects on the magnetic sensitivity and offset of CMOS Hall sensors. But it is also the poor performance of bipolar transistors in standard CMOS technology. And we do have an existing processing chain with a differential ADC, a microcontroller, and a regulated 3.3 volt supply. So basically our system works the following way. First we measure 4 Hall phases, followed by a reading of the temperature sensor, and followed by a reading of an additional input signal. So we could summarize the temperature sensor as follows. We need a 3.3 volt supply, which we have available, and it must have a differential output signal. And a very simple structure providing this is a resistive. However, when using resistive resistors for low stress design, we have to take into account the piezoresistance effects. So for example, if we do low stress design, then we found that the combination of P-well and P-poly material is favorable. However, we have to have still a closer look to the piezoresistance effect. And for example, when looking at a P-well resistor which is aligned parallel to the wafer flat, it shows a very high anisotropy. And this is the main feature used in MEMS pressure sensors, for example. Well, if they're based on piezoresistors and not capacitive ones. As a first step, what we can do is we can rotate the resistor to 45-degree orientation. And in this way, the longitudinal and transverse piezoresistive coefficients already get smaller in magnitude, and also the difference between those two gets smaller. As a further step, we can build L-shaped resistors, which are orthogonal resistor pairs. And in this way, we obtain isotropic piezoresistive response. Now this was shown now for the P-well resistors. We can apply a similar procedure for the P-poly resistors. Here also we find quite a large difference between the longitudinal and the transverse piezoresistive coefficients. And in a similar way, we can form L-shaped resistor in order to obtain isotropic piezoresistance with respect to in-plane stresses. Now to summarize this, we form orthogonal pairs for the P-well and the P-poly resistors. And what we obtain by doing that is we have small piezoresistance coefficients, and they are nearly equal between the two of those materials. However, resistors can show quite big mismatches, and this is what we will discuss next. So, first of all, upon a mismatch between P-well and P-poly resistors, this would immediately lead to some offset in the output signal. There is, however, a more sophisticated problem which comes from the depletion of the P-well resistor. On the left-hand side, there is schematic of an L-shaped P-well resistor combining perpendicular and a parallel resistor. And on the bottom left, I show a cross-section through those two resistors. From that, it is obvious that one of the resistor, the one at the lower potential, suffers more from the depletion than the other one, which is at the higher electric potential. And this, after all, would lead to that the resistor, the perpendicular resistor, is not equal anymore to the parallel resistor and show as an anisotropic behavior in piezoresistance. And this is an unwanted effect. There is a simple solution to that problem, and in this simple solution we combine two L-shaped resistors to a double L. And in this way we obtain that the sum of the two perpendicular resistors equals now the sum of the two parallel resistors, and we have re-established the desired isotropic behavior. Now, so this summarizes the basic design concept that we applied, and on this slide I would like to show the schematic of our temperature sensor. We can summarize the design as we combine P-well and P-poly resistors because they show a small difference in piezoresistance. P-poly here shown as in green color and P-well in blue color. Second, we rotate the P-well resistors to angles of plus minus 45 degrees. In this way, we minimize the difference between the longitudinal and the transverse piezoresistance coefficients. Third, we combine resistors to orthogonal pairs in order to obtain isotropic piezoresistance. And fourth, we combine two resistor Ls in order to minimize the impact from the junction field effect. The implementation was done in a standard 0.18 micrometer CMOS technology. Here we implemented 16 individual resistor segments. Each of the segments has a resistance of 10 kilo ohm. And so the total resistance of the bridge is 40 kilo ohm, and at a bias voltage of 3.3 volt, it draws a current of 82 microamps. On the right-hand side, I would like to show the actual layout of the temperature sensor. In the center, we have the P-well resistors at plus minus 45 degree angles, and they are surrounded by the P-poly resistors. The overall size of the temperature sensor is 63 micrometer by 63 micrometer. We characterized the temperature sensor on a 4-point bending bridge. In this way, we can apply defined mechanical stress along our samples. This entire setup was placed inside a climate chamber in order to accurately control the temperature to 25 degrees Celsius. What we can obtain from that measurement are the piezoresistance coefficients for the P-well and the P-poly material. For the P-well material, it is in line with the values expected from literature. However, it is quite interesting to see that the longitudinal piezoresistance coefficient and the transverse piezoresistive coefficient for the P-poly material are quite different. And so this proves actually that we really also have to implement the P-poly resistors as orthogonal pairs. Next, we analyzed the stress sensitivity of different types of temperature sensors. We analyzed it for the preferred P-well P-poly structure, but also for a similar N-well P-poly resistive bridge, and also for a conventional P-TAT cell based on PNP bipolar transistors. What we obtained from that measurement is the stress drift of those three different temperature sensors at different values of mechanical stress. And for 60 megapascal of tensile stress, we measure for the N-well P-poly resistive bridge an error of the sensor output of minus 4.4 Kelvin. For the P-well P-poly bridge, it is about 10 times less, minus 0.47 Kelvin. However, still the smallest sensitivity to mechanical stress was demonstrated for the conventional P-TAT cell based on PNP bipolar transistors. Finally, we measured the thermal response of our sensor for samples assembled as chip on board, so they're considered to be stress-free, and also for packaged samples in order to have realistic stress values. We measured a thermal sensitivity of 3.9 millivolt per Kelvin at 25 degrees Celsius and 3.3 volt supply, and we see quite a nonlinearity which is related to the second order TC resistance of the P-well material. Also, we measured an offset of 500 millivolt, which comes from the mismatch between the P-well and the P-poly resistors. However, still, it is remarkable that with this structure, we can obtain a differential output signal of 700 millivolt for a temperature change from minus 50 degrees Celsius to plus 130 degrees Celsius. So with these results, I would like to end the experimental section and go to the last slide, which are our conclusions. So we demonstrated a sensor, temperature sensor that provides a differential output with a sensitivity of 3.9 millivolt per Kelvin. The sensor needs calibration, certainly for the offset, but potentially also for the sensitivity and the linearity. It has a small size of 63 micrometer by 63 micrometer, and it is compatible with standard CMOS technology. We could confirm the small stress sensitivity to be as small as 0.007 Kelvin per megapascal. Thank you very much for your attention.